So, um, examples now, just to solve more examples relating to the Taylor and Maclaurin series. So the reason we discuss the polynomial is to see how we can build the series. Okay, the series is majorly our business anyway. So let's say this problem. It says obtain the Maclaurin series. Obtain the Maclaurin series for 1 over 1 minus x. Okay, so we have this function. We want to have its expansion. All right, we want to see the infinite series representation of this function. Okay, it already told us it's Maclaurin series, so we don't have to bother about x naught. We know x naught is 0. And we know if we are not even interested in that, we already know the formula for that. Okay, so basically, solution. I said I don't want to draw that line again, so let's try the solution here. All right, so we are given now that f of x is equal to 1 over 1 minus x. We know that we will need f prime of x, that's the derivative of this, and we know this derivative is going to be 1 over, I mean, that is bottom the top minus top the bottom of the bottom square. We know the derivative of the bottom is minus 1, derivative of 1 is 0, derivative of minus x is minus 1. So bottom the top, that is this multiplied by derivative of the top is 0. So basically we're going to have this to be minus top the bottom, derivative of the bottom is minus 1, so that will be minus of minus 1 all over bottom square, that is 1 minus x all squared. So this is going to be equal to 1 because minus of minus 1 is 1, 1 over um, 1 minus x all squared. Or if you like, we can write this as 1 minus x to the power of minus 2. So it's easy to get the next derivatives. F prime prime of x will be equal to derivative of this. Just move down the minus 2, then reduce the power, move down the minus 2, multiply by derivative of what we have inside. Derivative of what we have inside is minus 1. So that is going to become 2 into this 1 minus x to the power of minus 3, and then the next one will be f prime prime of x. That will be 2 multiplied by minus 3. This minus 3 when brought down multiplied by minus 1, so this is 2 multiplied by 3, basically that's a 6 into 1 minus x to the power of minus 4. And if we observe the next derivative, so we just want to come up with a pattern anyways, so let's come up with a pattern that's quite easier to deal with that way. The fourth derivative will be 6 multiplied by, it should be 6 multiplied by minus 4, then the derivative of the core, what we have inside here will still be minus 1, so that is just 6 multiplied by 4, which is 24, and that is going to give us 1 minus x to the power of minus 5. So basically we already know what the derivative of this should be. We can already see a pattern, and we can say that of course the nth derivative of x will obviously be equal to, we can see this is 2, this is 6, this is 24, this is 1. So we see that the first derivative here, is simply what do we call that now? The first derivative here is simply having its coefficient to be 1, which you can call 1 factorial. This is 2, which you can call 2 factorial. This is 6, which you can call 3 factorial. This is 24, which you can call 4 factorial. The next one will be 24 times 5, which you can call 5 factorial. So basically, this is going to be n factorial, then multiplied by this. So we can put that in the denominator into 1 minus x, then raised to the power of this is 5 when x is 4, when n is 4, this is 4 when n is 3, so this is going to be n plus 1, okay, because for n equal to 4 this was 5. All right, so with this we know this is the general expression for the derivative of the function f of x, but basically we know that in our expression we need these values at x equal to 0. Okay, so it should be quite easy to get at x equal to 0. Okay, so when x equal to 0, we can get what the derivatives will be. So at x equal to 0, we're going to have the nth derivative. We want to get the general expression, if possible, at x equal to 0. Just substitute x equal to 0 here. That will be n factorial divided by, this will be 1 minus 0 raised to the power of n plus 1. This is 1, okay? Whatever this is just going to be equal to n factorial. And of course, that is obvious here that if you substituted what is now 0 here, this is going to be 1. If you substituted 0 here, this will still be 1. If you substituted 0 here, this will be 1. So, and that will continue like that, or like that, and like that. So we can just simply say that it is going to be n factorial. So with this, we are good to go. We know that our Maclaurin series, so recall that the Maclaurin series for f of x is given by, write out the general expression again. It's a lot easier to just use the general expression instead of getting the terms one after the other, which is going to take time. So it's given by f of x equals, that's the Maclaurin series expansion from k equals 0 to infinity x to the power of k divided by k factorial, then multiplied by what is this now, f, and that's the nth derivative of f at x equal to 0. So we can expand this out. We know that the first term will be when k equals 0. So when k equals 0, this will be, okay, let's substitute all of these things first. So we know f n at 0. So we can say this is, sorry, this is f k, that's the kth derivative at 0. Okay. So we know the n derivative at 0 is n factorial. So the kth derivative at 0 will be k factorial. So basically this is going to be equal to uh, the summation. So we can substitute directly from k equal to 0 to infinity of x to the power of k divided by k factorial multiplied by f, that is the kth derivative of f at 0. We know the nth derivative of x at 0 is n factorial. So the kth derivative of f at 0 will just be k factorial. So this will just be multiplying k factorial. And obviously this will cancel this out. So basically what we have left will be the summation from k equal to 0 to infinity of x to the power of k, of x to the power of k. So that's interesting. Very, very, very interesting. So that is our answer. We can leave it like that. So we can have, if this was a multiple choice question, for instance, we can have one of the options to be just this. So you know what exactly it is. It can't be just x to power k. It has to be this summation. So we say that if you like, you can expand that out. So this says from k equals to 0. So when k equals 0, this is x to the power 0, which will be 1, plus when k is equal to 1, that will be x to the power 1, which is x, plus when k equal to 2, that will be x squared, plus when k equal to 3, that will be what do you call that now, that will be x to the power of 3, sorry, yeah, x to the power of 3, plus when k equal to 4, that will be x to the power of 4, plus and so on and so forth. To continue like that forever. That has no end, so we're not putting any end there. So basically this is the Maclaurin series for the function uh, f of x equals 1 plus 1 over x. So this gives us an interesting result anyways. If we observe this series, for instance, we know that for this particular series, this expression is, um, if we observe the characteristic of this series, this is a geometric series, or geometric progression. Okay, you should know about geometric progression already. Geometric series is of the form. I just want to make some observation around what we've done here. This is our results. This is everything that's required by this problem. So we are done basically. So, but we just want to. I just wanted to notice something about this result. You should observe that this is a geometric series. Don't forget that a geometric series is when you have the terms or the sequence of terms, or yeah, the terms of sequence, if you like, to increase geometrically by to increase or decrease by a common ratio. So if you have the first term, for instance, to be a, The next term is going to be AR. So this is R, which is common ratio. The next term will be AR squared. The next term will be AR cubed. That's what we call a geometric progression or geometric series. So that's exactly what we have here. If A was 1 and R was X, this will be 1, and the next one will be X. The next one will be, this is 1 times X, this will be X. 1 times this x times x will be x squared, x times x squared will be x cubed, and x to power 4 and x to power 5, and that will continue like that forever. That is telling you that the terms of this series are make form a geometric progression, or this is a geometric series precisely. Like I said, we have a separate course where we discuss series, frequencies series, and power series. When we get there, you see all of this in details. But this observation is very, very, very important. Okay, so you will notice something here, that this is a geometric series. Now, there's something also for geometric series that we call the sum to infinity of a geometric series, and the formula was a over 1 minus r. Okay, if you can remember these, or just revise some of the things you learned from elementary mathematics on this, you should recall that this is the expression for the sum to infinity. So if we were to use that for this geometric series where a is equal to 1 and our r is equal to x, we know that this is going to be a, which is 1, over 1 minus r, which is x. So this is this is 1 over 1 minus x, which is in this case the function that we were given. So you see that the function is 1 over 1 minus x. So this is a very important result in mathematics. It's just the sum to infinity of a geometric progression. And from what we have also learned in elementary mathematics, we know that this is only valid, but the sum to infinity only exists when the common ratio has a modulus that is less than 1. Okay, so this is only valid when the modulus of x is less than 1. And of course, if modulus of x is less than 1, from what we have done just now, we know this means minus r is less than x less than 1. So that means x lies between minus 1 and 1. And what is that? Between minus 1 and 1, that is around 0. So this is only valid around 0. So once you go outside that, it won't be valid. The values will be very far apart or far away from this. But this is sufficient to actually capture the idea. This is telling you that this expression here is an approximation for the function f of x, okay, around x equal to 0. So around x equal to 0, this is going to give you exactly f of x around that value. But this concept is just showing us that this is only valid here around x equals to 0, and it is best fit when you have that distance from 0 to be within 1. Okay. All right. So let's forget about that. This we've solved the problem already. So let's just move on. Okay. So let's consider another problem here. We've been told to obtain this another question now. Another question. Obtain the Taylor series. Okay, I call it Taylor series and Maclaurin series. So it's not wrong to write Taylor's series. It's fine. Okay, I just think that um, this is I'm just more at home with the terminology written this way. So Taylor series expansion. Obtain the Taylor series expansion of cos x, okay, about pi over 3. So about the point pi over 3. So solution. So we already know that this is Taylor series and not Taylor series at x equal to 0, about x equal to 0. If it was about 0, that's Maclaurin series. So that means that in this case, we have been given that f of x equals cos x, that's our function, and we have also been given the point x naught to be pi over 3. Again, what do you think is the best way to approach this? The best way to approach this is to find the nth derivative of the function. We know that f prime of x is minus sine x. We've seen this several times. We know this is just going to be cos x plus pi over 2. And of course, from what we've done before, we know that the nth derivative of cos x is just cos of x plus n multiplying pi over 2. All right, so we know this is exactly what we need here. Okay, if we didn't have this before, we could just find it out. So basically we know then that generally the nth derivative of x at our x naught now, at x naught, is the nth derivative of f at x equal to pi over 3. Okay, so I just want to put that in. That will be equal to the cos of what is that, pi over 3 plus n pi over 2. Okay, so that's the expression. Let's see, can we simplify this further? And say this is cos of this is 6. The denominator, the LCM of the denominator is 6, so this will be 2 pi minus 6 n pi. All right. Does that simplify our work in any way? No, it doesn't. So let's leave it like that. Let's leave it this way, okay? And just to move on. So we know this is our nth derivative at any point. And now, therefore, our by our Taylor series. So just let's just recall that formula. Recall that the Taylor series expansion of f of x around or about or at x naught is given by this expression. What is that expression? That expression is f of x, recall, equals the summation from k equal to 0 to infinity of, what is that again? That was x minus x naught to the power of k divided by k factorial, then multiplied by the kth derivative of f at x naught. All right, so this is the expression we're going to use now. We have our parameters already, the things that we need, we have them already, so we can just insert them directly. So let's do as much simplifications as possible before the expansion, so that by the time we do the expansion, we know it will be quite straightforward or easy to get the various terms of the expansion. So let's retain this first. So this is summation from k equal to 0 to infinity of x minus x naught to the power of k divided by k factorial, then multiplied by this. We know that this is going to be f of x now. It has been expanded about x about pi over 3. Okay, so for the expansion about pi over 3, our x naught will be equal to pi over 3. So we can identify that, but x naught equals pi over 3. So therefore, we're going to have this expression, and this is going to be equal to f of k, okay, at pi over 3, which we already found here. Okay, so this is going to be equal to the summation from k equal to 0 to infinity of x minus x naught to the power of k, x minus x naught to the power of k divided by k factorial, then multiply by this. This is multiplied by cos of pi over 3, pi over 3 plus n pi over 2, pi over 3 plus n pi over 2. All right. So that's the expression. There is nothing to cancel out here, so it just works like that directly. And we can now find out, just write out the first few terms. We know this is the general expression for it. Oh, did I still retain x naught? X naught is pi over 3, so this should be pi over 3, and this should be pi over 3. Okay, so that's our expression. So this is pi over 3, this is pi over 3. With this, we can say that this is going to be equal to, we can just write out the first few terms. We know that when k equals 0, this will be 1 here, and this will be 1, so we can forget about that. We're going to have cos of, this is cos of pi over 3, because this expression will be 0. So let's get cos of pi over 3. Cos of pi over 3 is 180 degrees divided by 3. That is, so of course our calculator has to be in radians. So let's just enter that. That is cos 60. Cos 60 is going to be 1 over 3. But let's see that this is shift, this is pi divided by 3, and get back to this, close the bracket, that is 1 over 2. So basically this is going to be 1 over 2. Okay, then plus the next thing here is when k equal to 1. When k is equal to 1, this will give us x minus pi over 3. So let's write that out first. X minus pi over 3. So raised to the power of 1, so we leave it like that. Then multiply by cos pi over 3 plus pi over 2, because that would be pi over 3 plus 1 pi over 2. So let's get back to our calculator. So let's write out this formula directly. So we'll just be inserting whatever our n is. Let's use this as alpha. If n, we just want to use n, we can use any other letter. Is there n here? We don't have anything like that here, so let's use alpha m. Okay, so m, then multiplying pi over 2, multiplying pi over 2 times pi shift pi divided by 2. So what we're doing here is that it makes it easy to just evaluate this expression for different values of n, which in this case we have represented as m. So we can just press calculate, and it asks us for the value of m we want to use. For instance, we can say it's 0. It gives us 1 over 2, which was what we did earlier. So we can just get that directly here. And when m is equal to 1, it gives us root 3 over 2. So this is multiplying. So multiply by, was that root 3 over 2 or minus root 3 over 2? Minus root 3 over 2, please. So this is going to be this multiplied by minus root 3 over 2, then plus when k equals to 2, that will be x minus pi over 3 raised to the power of 2 divided by 2 factorial, which is 2. Okay, let's write it out first. Then, that goes from here. Okay, this was 1 factorial, so it was 1, so that was why we didn't need to write anything here. Then this will be cos of this when n is equal to 2. So when n equal to 2, let's get back to our calculator. Calculate what happens when n equal to 2. This is minus 1 over 2. So this will be dot minus 1 over 2. Then plus what happens next? That will be x minus pi over 3 raised to the power of 3 divided by 3 factorial. Then multiply by what happens when n equal to 3. So let's calculate that. When n equal to 3, calculate when n equal to 3. This is root 3 over 2. So you can see this is going to be root 3 divided by 2. Then plus what happens when n equal to 4? This is x minus pi over 3 to the power of 4 divided by 4 factorial, multiplied by what happens when n equal to 4. Let's do that. Calculate when n equal to 4. This is 1 over 2. So this is going to be multiplying 1 over 2. Then plus the next term will be x minus. I'm going to stop here. We can continue like that and just keep getting that. Divided by 5 factorial, multiplied by what happens when n equals to 5. Let's get back to this. Calculate for n equal to 5. That's minus root 3 over 2. So this is going to give us minus root 3 over 2. And the terms will continue like that. Okay. So let's just tidy this up. We're going to have this to be equal to, of course we can expand, but we'll just leave it like this. This is going to be 1 over 2 plus this is root 3 over 2, let's say minus is outside, so let's say minus of root 3 over 2 into x minus pi over 3. Then the next one is also minus 1 over 4. Okay, this is 2 multiplying 2 factorial, that is 1 over 4 multiplying x minus pi over 3 all squared. Then plus the next one here is going to be x minus, that is x minus pi over 3 to the power of 3, then divided by 3 factorial. This is root 3. This is 2 times 6, that is 12. So let's write root 3 over 12. This will be plus root 3 all over 12 multiplied by x minus pi over 3 raised to power 3. And that continues like that, like that, and like that. Okay, so we can keep examining that and just writing them out. But what's important is we know the formula, we know the expression for it, so we can expand forever. So we know it's an infinite series, but that is the representation of our function f of x equal to cos x. That is our Taylor series expansion of f of x equal to cos x about the point pi over 3. Okay. So, thank you for watching. We'll proceed from here in the next lesson to consider other examples.